Okay, so this is lesson 3, and to recap what we said last time about pH, we had stated that pH is a measure of the hydronium ion concentration in a solution. When we think about that, we think about H+. And we also said that each pH difference is a 10-fold change. So let's build upon that in this lesson. The easiest method to use for comparing the strengths of acids and bases is pH. We test our fish tanks because fish pee out ammonia, which is a base, and brings the pH up. So if the pH is too high, then we need to add something to it to lower it down. Our lawns tend to be a little bit more acidic because acid rain brings the pH of the soil down. And sometimes we have to add something to our soil to neutralize the acid rain. And even food is pH tested as it is being made to make sure that it falls within a specific range. You wouldn't want your super sour candy to have too little bite, would you? So just what is pH and how do we use it? So, as you know, we said that pH is a measure of the hydronium ion concentration. Our pH scale goes from 1 to 14. What you need to remember is as we go to the left of 7, these are our strong acids. And as we go to the right of 7, these are our strong bases. When the pH is 7, our H+ concentration equals our OH- concentration. Anything to the left of 7, H+ is greater than OH-, and anything to the right, our H+ is less than our OH-. When something has a pH of 1, we say that its molar concentration is 1 times 10 to the negative 1. If its pH is 2, then the pH is 1 times 10 to the negative 2. And I'm reading along the bottom of the scale. Right here. When our pH is 3, our molar concentration is 1 times 10 to the minus 3, so on and so forth. Notice as we go into base range, our H concentration is 1 times 10 to the negative 14th. That's really, really, really very little. It's a very small number. And then you can see on the top is our hydroxide concentrations. Our whole scale has to equal 14. Now, the hydroxide concentrations are there, but we don't usually refer to them. Everything is measured from the hydrogen or hydronium concentration. So here you can see when the concentration of H+ is 1 times 10 to the minus 10, then the pH is equal to 1. And there's some more examples there. And then at the very bottom, we talk about the change. We revisit that again in pH. So a solution with a pH of 3 is 10 times more acidic than a solution with a pH of 4. A solution with a pH of 3 is 100 times more acidic than a solution with a pH of 5, because that's 2 pH values, or 10 times 10 on this one. And then on the bottom, a solution with a pH of 6 is 1,000 times more acidic than one with a pH of 3, and that's because that's 10 times 10 times 10. In this slide, we're specifically talking about bases, and when we add bases to water, we decrease the hydronium ion concentration so that the pH decreases by 1 as the base strength increases tenfold. So, for example, when the concentration of OH minus is 10 to the minus 1, then the pH is 13. When the concentration of OH minus is 10 to the minus 2, it's a pH of 12. So there's two things. The pH, the exponent tells you the actual pH value, and they don't usually ask that on the Regents anymore, but you have to pay attention to whether they're talking about H or OH. And then looking at the strength, a solution with a pH of 13 is 10 times more basic than a solution with a pH of 12. A solution with a pH of 13 is 100 times more basic than a solution with a pH of 11, so on and so forth. And then here's some common pHs of substances. You can see that all of your cleaners, your household bleach, ammonia, soap, are all in the base range. Seawater is slightly basic, and then you've got potatoes, carrots, grapes, orange juice, apples. They are a little bit more on the acidic side, which was what we would expect of fruit or vegetables. And this page actually recaps what I said in the first lesson. We have Arrhenius acids and bases. An Arrhenius acid produces H plus as the only positive ion in solution, and Arrhenius bases produce OH minus as the only negative ion in solution. That's right there. Now, there is another theory which is referred to by the Regents at this point in time as the other theory. So this is the Bronsted-Lowry theory, but I want you to realize that Bronsted-Lowry is the other theory, because that's what the Regents refers to it as. Don't ask me why. They used to refer to it as Bronsted-Lowry, and then they changed their name. And in this theory, it says that acids are proton donors and bases are proton acceptors. And you actually have to look at what's happening. In this first example here, you have H giving up, or you have HCl giving up its H to H2O, right? It gave up an H and formed H3O. So that makes HCl the acid because it's the proton donor. The reason why H plus is called a proton donor is because that's all it contains is a proton. The base is accepting the H, so it becomes the proton acceptor. In this second example, you have H2O giving up the H to NH3, forming NH4. So in this case, water acts as the acid and NH3 the base. But in this last example, you have acetic acid, which is vinegar, giving up its H to H2O, forming H3O, and the water acts as the base and the acetic acid as the acid because it donated the proton, sorry. So notice how water can be an acid or a base. And that's because it's considered amphoteric, which simply means that it can either donate an H or accept an H. And what we have to look at is acid-base pairs. In higher level chemistry, this is called conjugate acid-base pairs. It's not important that you know the name at this level, but whatever you identified as the acid on the left side has a base pair on the right side. So here HCl lost an H or gave it up to water and formed Cl minus. So here HCl is the acid and Cl minus is considered a base. The water gained the H, so it's considered the base, but when it formed H3O, this is considered the acid. So everything has an acid-base pair in all of these. NH3 goes with NH4, so this is the acid, and here's your acid as water, so your OH minus is your base. And then the last one, your acetate, your acetic acid gave up its H, the acetate ion is the base, and the water gained the H, so the hydronium is the acid. Fairly straightforward and easy, the stuff in this unit.